Welcome back to UTEP Intro to Electrical and Computer Engineering, Fall 2021. I'm Dr. Roberts. We are doing practice problems, and this is practice problem 8 from this week. This is the last problem. And if you've been following along, and if you haven't been following along, and this immediately looks challenging to you, go back and start watching with practice problem 6. We first derived an understanding of a op-amp here where there's a single resistor in the feedback and a single in the input, right? And if we compare that here, well, now there's just two elements here, but very similar. So go do that problem first, go watch that video. And then you can watch problem 7, where see, after problem 7, we put two resistors in parallel, very similar to this circuit actually, right? And we saw what the behavior was, right? And we saw that the gain was exactly the same as in problem 6, except just changed with the resistor values, and we derived that out. And we also expanded then that parallel equation. So now, if we have the same circuit as problem 7, but we have a capacitor, what do? Right? We don't panic, right? That would not be good. But the first thing we should always do is use phasors, right? And if you're rusty on phasors, if you go back to an earlier video in this series today, right, I explained phasors again. So if we use phasors, we can make everything a resistor essentially, and we just change the values. And I like to redraw my capacitors as resistors at that point, just to remind me. I'm drawing this really weird for whatever reason when I'm redrawing it. I'm doing it live. Sorry, forgive me here. My feedback loop looks weird. I got busy, distracted about talking, and can't draw and talk, right? So in the phasor domain, resistor stays resistor. So R1 becomes R1, R2 becomes R2, and C2 becomes 1 over J omega C2. But now, even though I drew this really weird, see, we all have our weird moments. We have these things, right, where this is V sub A. So now I just have two resistors in parallel, where one is a complex resistor, the capacitor, and now we can do the exact same things to solve. Man, this is really weird looking in that way, right? So we notice these are in parallel, so now we can combine them. So we can now redraw it again, and maybe let me do a good job this time. So let me focus on drawing while I'm talking to you. So hopefully it doesn't look super crazy. Oh man, already messing up that resistor. Right. Like this, V out, this is VA, and this has then a value of R2 parallel 1 over J omega C2. Right, so now this has been reduced down to problem 6, right, which was like we did in problem 7, and now we can solve, right? So I can say, okay, that the current here is I1, the current here is I2. I can now, at VA, what do we know, right? Ideal op-amp, we know that IN is equal to 0, IP is equal to 0. We know that VN is equal to VP by definition. So we know that 0 volts is equal to VP is equal to VN is equal to VA. So from there, we know that VA is equal to 0 volts. Now we can do KCL at node A, just like last time. And if we do that, I1 is going in, so positive. I2 is going in, so positive. IN is leaving, or I didn't draw it, but we could have it leaving. It's equal to that, but IN is equal to 0 anyway, so it doesn't matter. So just like in the last two examples, we get that I1 is equal to negative I2. Now we can use Ohm's law to our advantage, right? And again, we can write relationships here. So I1 is going to be equal to V top minus V bottom. So it's going to be equal to Vn minus VA over R1. And we know the VA is equal to 0, so that's going to be equal to Vn over R1. And we know that I2 is going to be equal to V out minus VA over that equivalent resistance, which is R2 parallel with 1 over J omega C2. And again, we know that this is 0 here. So just like in the last problems with the last two examples, we can now substitute in. So we get that I1 is equal to Vn over R1, and that's equal to negative I2, which is here. So that's going to be equal to V out over R2 parallel with 1 over j omega C2, just like that. And we can rearrange and see that, just like we did, right, that V out over Vn is equal to, I'll write it the same way as last time, minus R2 parallel 1 over j omega C2 over R1. Right? Where we can also then again rewrite this as minus 1 over R1 times this quantity of R2 parallel 1 over j omega C2, which I did in the last problem. Now, this is inconvenient. Let's expand this. And what we know for two parallel elements, two parallel resistors, right, that R2 parallel 1 over j omega C2 is going to be equal to R2 times 1 over j omega C2 over R2 plus 1 over j omega C2. Right? The exact same thing they did with two resistors. We just have one's more complex. But this is ugly still. So what I'd like to do then is let's multiply through by j omega C2 times j omega C2 to clean this up. So this will multiply in up here. This will multiply across here. So if we do that, we get that R2 parallel to 1 over j omega C2 is equal to, these cancel, so is equal to R2 over j omega C2 R2 plus j omega C2 over j omega C2. I simplified this one out. This fraction's 1, but we'll do it here. I'll leave it here. 2 over j omega C2. Right, this is 1. This is 1 here. So we get that R2 parallel 1 over j omega C2 is going to be equal to R2 over j omega R2 C2 plus 1. Well, now we can move this down here, and we say that V out over Vn is equal to negative 1 over R1 times this quantity, R2 over j omega R2 C2 plus 1, like that. I'm just going to move to another page here. So, okay, we've expanded out. And let's move things around. Just for fun, let's move this R2 over here. So if we do that, we see that V out over Vn is equal to minus R2 over R1. And then this over here is 1 divided by j omega R2 C2 plus 1. Okay, so this is then the relationship, which is part A. Check. But what does this tell us? Let's look at this, right? What do we see? If I would look, so here's the circuit. Let's see, right, move things around here on the screen. Well, wrong one. I've got too many problems I'm working here, right? So here's the circuit here, and here's the transfer function. Now, if I would go to the simpler case of just two resistors in parallel, I get this relationship, right? So if you have a resistor, the feedback resistor, and the input resistor, the gain is negative R2 over R1. Now, in our problem here, we have the same R2 and R1, and we still have the same gain, right? So here, we have some gain of our amplifier. But then I also have this extra term. This extra term, well, let's see what's going on, right? So if omega is equal to 0, this whole term here is 0. 0 plus 1 is 1, right? So in that case, 1 divided by 1 is 1. So at 0, then V out over V in is equal to minus R2 over R1. So times 1, right? And so at the output, it passes through with some gain. And if we look at omega is equal to infinity, here we have infinity. Infinity plus 1 is infinity. 1 over infinity is 0. We get that V out over V in is equal to minus R2 over R1 times 0, which is equal to 0. So it passes here, and it's blocked here. So now what do we have, right? We have that behavior is a low-pass filter behavior, right? It's passing a low frequency. Now, and there's some gain here. So we would call this an active low-pass filter with a gain of minus R2 over R1 and a cutoff frequency at f sub c is equal to 1 over 2 pi R2 C2. Now that's interesting. See, so the combination of resistor sets our gain, but then the capacitor and only R2 set our frequency. So we can independently tailor our gain and our frequency. So that's what's really happening here. And all we did was substitute a capacitor. So not only do we get the same low-pass filter behavior we saw in a previous practice problem, we also get the gain behavior of the op-amp. So we get the best of both worlds. That's pretty interesting. Pretty cool, right? We're only using a couple components. So hopefully this was helpful. And if you have questions or that, feel free to send me an email, and I'm happy to clarify. Have a wonderful day.